Let's continue with our discussion on the design of reinforced concrete structures. We are in chapter 1 and these were the contents of chapter 1. In our previous lecture we discussed on the introduction to reinforced concrete structure and then we discussed on characteristic strength and loads. Today we will look at the remaining 2 points. That is, first we will look at the design process and the basis for design, and then finally we will see the different design philosophies or design methods of reinforced concrete structures. So let's begin today's lesson. So here I have presented a rather simple chart that depicts the design process of any reinforced concrete structure. There are 5 main steps as you can see in the chart, and the first step is the adoption of a structural system. Structural system means what types of structural elements do you want to build so that the loads coming onto that structure is resisted by that system. You may adopt a simple beam column slab system, which is a system generally known as the moment resisting frame option, or you may want to include the shear walls in addition to the beams or columns. That is generally referred to as the dual system. That means in which you have both shear walls and the moment resisting system. Or in case of very tall buildings, you may want to adopt unique or very particular kind of structural system suitable to that tall building. So adopting a structural system may be a very important case in case of complex buildings and complex structure. And adoption of a structural system is generally dependent on the knowledge and experience of the designer. So once you decide the type of structural system to be used, then we go to the preliminary analysis of that system. And in the preliminary analysis, we make various approximations. We estimate the loads coming onto our structure, and then we try to find the general behavior of our structural system to those estimated loads. The third step is the proportioning of members and their connections, foundations, and other various elements. So for proportioning of these members or for determining the cross-sectional sizes, for determining the reinforcement in various members, you have to make use of various design criteria. And those design criteria is you generally get that design criteria from the code of practice that you follow to design the structure. The foundations can be designed based on the data contained in the soil test report, and you also may follow various codes and specification. After the proportioning of members, you do a more exact analysis, and that exact analysis is generally performed by the use of computer programs. In doing an exact analysis or in doing analysis using those computer programs, you may adopt different methods. You may adopt for a linear analysis, or you may go for a non-linear analysis, or you may go for a performance-based design. Various types of analysis methods can be adopted for analysis using computer programs. And finally, you perform the evaluation and final design. So these are the 5 steps related to the design process. So here you can see another chart representing the design process. So the process here, you can see that it starts with a conceptual design, and conceptual design involves the selection of primary shape and form of structure, as well as selection of gravity and lateral load resisting elements. So this conceptual design phase is probably the most important step because it affects the overall performance and the final outcome. In this conceptual design, complete architectural functional plan is developed in this very first phase. So once you select the right structural system, then the next stage is to go for the modeling and analysis. And in modeling and analysis, this step is used to find the expected response of a structure under different kind of loadings. So we perform modeling and analysis. First, we start with different trial sections, and we perform or we construct an idealized model in the computer software that may be available to us. So that we select a particular analysis process, and we adopt a particular code of practice or standard that helps us in modeling and analysis. So these modeling and analysis results are then used for the design of various members. As you can see, as we discussed in our previous lecture, analysis gives us the various load effects, the various internal forces that act on the different structural elements that we call as response, and that response quantities are used for the design of various members. In designing, if the design of the member is acceptable, then we go to the detailing, or if it is not acceptable, then we go to the revising of members and sections. We revise the cross-section sizes of various member sections, and then we perform the modeling once again, and then we go to the analysis process once again. So this process is repeated until all the elements are given an acceptable design. And once we get an acceptable design, we go for the detailing, and this detailing process finally leads us to the final design output. And if needed, we may also perform cost analysis. We may want to, or the client may want to know the estimated cost of that structure. That cost can also be derived after getting the final design output. So this is a general process that depicts the design of any structure, or in our case, the design of a reinforced concrete structure. So this is about the design process. And what are the design considerations? Our design considerations can be many. For example, safety, stability, serviceability, economy, durability, and many more. These design considerations means those facts that a designer keeps in mind while designing the structure. So the primary consideration is that the collapse of the structure should be acceptably low. That means our structure should be safe, and that safety should be guaranteed not only under the normal expected loads, but also under the less frequent loads like earthquake or wind, or some accidental loads like blast loads and other. So our structure should be safe. Our structure should be stable. That means even when there may be a partial collapse or collapse of a certain part of our structure should not be unstable as a whole. The redistribution of forces should take place so that the stability of the structure is that stability still remains there. Our structure should be able to perform satisfactorily under service load without causing any discomfort to the user. That means our structure should be serviceable. Our structure should not only be safe, but it also should be economical. Economical in the sense that not only in the initial building cost or initial design cost, but also including the life cycle cost. That means the cost that may be incurred during the design life of the structure, including repair and maintenance cost. And finally, our structure should also be durable. So these 4 or 5 points are the various design considerations that a designer must consider in this reinforced concrete design or the design of any structure. Now let's go to the design methods or design philosophies. So we saw that in our previous slide, what we came to know is that the primary objective or the primary purpose of a structural design is to create a safe and functional system. And in creating a safe system, in the course of time, various design philosophies have been adopted at various points of time. And all the primary thing about design philosophies or these design methods is that these methods or philosophies they recommend the use of some safety factor so that our structure is safe under overloads or expected loads that may come onto our structure during its lifetime. So the margin of safety is at the root of these different design approaches, and the way to calculate this margin of safety is what divides the design methods or design philosophies into different types. And the first design method that we are going to talk about is the working stress method or the allowable stress method. So this is the traditional method of structural design, and this is not only used for reinforced concrete structures, but also for structures made from other elements or other materials such as steel and timber. This method primarily assumes that the structural material behaves as a linearly elastic manner. You can see in the second point here, the structural material behaves in a linear elastic manner, and we can ensure an adequate safety by restricting the material stresses induced by the expected working loads on the structure. So that means there is always two sides to an equation governing the design, or that is concerned with the design of our structure. Let's say that the left hand side is the demand side and the right hand side is the capacity side. Demand means the load effects, or the effects that the loads create on our structure, the internal forces that various loads generate on our structure, or the magnitude of load that should be resisted by our structure, that is known as the demand imposed on our structure. Whereas capacity means the capacity of our various structural elements to resist the internal forces or to resist the loads coming onto our structure. So this capacity is dependent on the dimensions of our cross sections of various elements and the amount of reinforcement or the amount of steel that is present in that member. So demand means the demand that is imposed on our structure or the internal forces imposed on our structure, and capacity means the capacity of our structure to resist that load. So we can say that for a safe design of our structure, this capacity should always be either greater or at least equal to the demand. So always capacity should be, let's say, greater than or equal to this demand. So what does this working stress method say is that to get the capacity of our structure, we have to know about the capacity of the material that is used in our structure, because since the capacity of any structural cross-section, for example, any beam or column, is dependent on its cross-section and its material of its cross-section, we can ensure that a structure is designed safe if we always apply loads in such a manner that the stresses that is induced in these material is less than the actual capacity of these materials. That means the stresses that are induced on this material is always ensured that they are less than the capacity of that material. That means we want to keep the stresses in a permissible limit, and that permissible limit of our stress is always less than the material capacity. So as the specified permissible stresses are kept well below the material ultimate strength. See this third point once again. The specified permissible stresses, that means the stresses acting on our material or on our member, are kept below the material ultimate strength. The assumption of linear elastic behavior is considered justifiable. So what we do here is we use a factor of safety in the capacity side of this equation here. And this factor of safety is given by the ratio of strength of material divided by permissible stress. So this factor of safety is used here in the capacity side of our equation. So this working stress method or allowable stress method means, this allowable stress means the stress on our material is always kept within an allowable limit or a permissible limit that is well below the material ultimate strength. So what is the drawback of this approach, or what is the negative point of this approach? Here, since we consider that the stress strain curve or the behavior of our material is always linear elastic in this method, but that behavior may not be actually true in the real life situations, since there are many factors that affect the elastic behavior and induce non-linearity in our material. The assumption of linear elastic behavior may not be always justifiable. For example, long-term effects of creep and shrinkage and other secondary effects may induce non-linearity in our structure. So this design approach, this working stress method, is such method that results in relatively large section of cross-sectional members or large section of structural member. That means larger width, larger depth, and thus this method provides us a conservative design. And although it is conservative, because we have used large sections, our serviceability performance under the working loads is usually better. So this is about the working stress method. So after working stress method came the ultimate strength method. So in this, the difference between the working stress method and ultimate stress method is that we saw this equation, demand and capacity equation, in our previous slide. What we discussed is that in working stress method, factor of safety is used on the capacity side of the equation. However, in this ultimate strength method, factor of safety is used in the both sides. That means both the demand and the capacity side. So the demand on our structure or the load effects on our structure is increased by a certain factor of safety by multiplying with certain factor of safety, let us say F1 here. And this F1 factor of safety is greater than 1, so that our total demand is increased, whereas the capacity of our material is generally reduced by using certain factor of safety F2. So this value of F2 is also less than 1, or sorry, greater than 1. Hence this right hand side capacity is reduced, whereas since the demand is multiplied with this factor of safety F1, which is also greater than 1, the demand is increased. So this is the difference between the ultimate strength method and the working stress method. So here in this ultimate strength method, the stress condition at the onset of impending collapse of the structure is analyzed, and the full non-linear stress-strain curve of concrete and steel is considered. For example, if you look at an example of a typical stress-strain curve for any material, for example, in the y-axis we have stress and in the x-axis we have strain. If this is our stress-strain curve, then you can see that some point here the yielding of the material begins. Till this point we see a linear elastic behavior for our material, whereas the yielding starts for this material beyond this yield point. So in our working stress method, only this straight portion was utilized. That means only the linear elastic behavior of the material was considered. But in this ultimate strength method, for example, if at this point the fracture of the material starts, or if this point represents the ultimate strength of our material, then the stress condition at this point of impending collapse is analyzed, and this whole non-linear curve of our material is utilized. So the safety measure is introduced by an appropriate choice of load factor here. In the previous slide, we saw a factor of safety given by the ratio of strength of material to permissible stress. In ultimate strength method, we have the load factor, which is the ratio of ultimate load over working load. So this value of load factor may usually range in between 1.2 to 2. So this ultimate strength method, by utilizing this full non-linear stress-strain curve of our material, what it does is that it makes it possible to assign different load factors to different types of load under the combined loading conditions. So as the full strength of the material or full capacity of our material is utilized, this method generally results in more slender sections. That means slender sections as compared to the working stress method, in which we had larger cross sections. So slender section means these designs are often economical for beams and columns, particularly when high strength reinforcing steel and concrete are used. And the drawback of this method is that because the structural sections are slender, the serviceability performance may not be satisfactory. Whereas in working stress method, because of larger cross sections, the serviceability condition was satisfactorily performed. Because of the larger cross sections here, the serviceability performance at normal service load may not be satisfactory. So this is about the ultimate strength method. And finally, the method that we are going to use in this design course, and the method that is now adopted, is the limit state method, which is an advancement over both working stress and the ultimate strength method. So limit state design concept is an advancement over both of the previous two methods. This method aims for a comprehensive and rational solution to the design problem. So it ensures safety at ultimate loads and serviceability at working loads. In the working stress method, we saw that calculations were made at service load condition only. That means the factor of safety was not used to increase the demand on our structure. In working stress method, we saw that factor of safety was used only on the capacity side of the equation to decrease the capacity of our materials below its ultimate strength, and then we suppose that the working loads were kept at this level of permissible stress or at this reduced capacity. So calculations were made on service load condition only. Whereas in ultimate strength method, you saw that calculations were made at ultimate load conditions by using the load factors. So working stress method considered only service load conditions, ultimate strength method considered only ultimate conditions, but in limit state method, we consider both ultimate condition and working conditions or working loads. So limit state method tries to ensure safety at ultimate loads and serviceability at working loads so that more than one safety factor is used. So this philosophy uses more than one safety factor to provide adequate safety at ultimate loads and then serviceability at working loads. So what this limit state means, the term limit state refers to a state of impending failure. That means it is a state beyond which a structure ceases to perform or it stops to perform its intended function satisfactorily in terms of either safety or serviceability. So limit state is a state of impending failure. Limit state method aims to ensure safety at ultimate loads and serviceability at working loads. Hence, we can say that there are two types of limit state. One is the ultimate limit state. That means these may be the limit states of strength, overturning, sliding, buckling, fatigue, fracture, etc. And another type is the serviceability limit states. That means in serviceability limit states, we consider the discomfort caused to the occupancy, and that discomfort may be caused by excessive deflection, excessive cracking, vibration leakage, or loss of durability. So in limit state method, what we try to do is we try to identify or recognize the different limit states of a building or of a structure, and then we select appropriate partial safety factors to ensure strength or safety at those limit states, to ensure safety at these ultimate limit states and the serviceability at working loads. So you can see here identification of all potential modes of failure, that is the significant limit states, and determination of acceptable levels of safety against occurrence of each limit state. So if you see the table here, different types of limit states are given. For example, ultimate limit state or serviceability limit state. And the third type, there may also be some special limit states, but we will ignore this for now. The ultimate limit states may be loss of equilibrium, rupture, progressive collapse, formation of plastic mechanism, instability, fatigue, etc. And design considerations are given for each of these identified limit states so that our structure does not fail in these states. And similar is the case for serviceability limit states that may include excessive deflection, excessive crack width, or undesirable vibration. So let's see in this chart here. This is the primary philosophy of working strength or allowable stress design method, in which the strength of the member, that means the capacity of the member, is reduced by using some factor of safety in this capacity side of the equation, and that is made equal to the A, means action due to loads or demand on our structure. So factor of safety is used in this strength side. Similarly, in ultimate strength design, the factor of safety is used in both sides here. The strength is reduced by using some factor of safety, whereas the demand on our structure is increased by using another factor of safety. Load factor design we will not be discussing, and finally in limit state method, different types of safety factors are used. and we try to identify different limit states. Limit state means the states of impending failure, and design considerations are given to those limit states to avoid those limit states in our structure during design. So these three are the design philosophies. But rather recently, a new type of design method, which is known as the performance-based design, is this performance-based design. The concept of performance-based design has come onto the field of structural engineering. So our design methods are usually code-based. Even our code for the design of reinforced concrete that we will be using in this course, IS 456, that is associated with this limit state design method. So these traditional building codes generally give us the performance objectives explicitly, and we cannot consider our own performance objectives. But in this performance-based design method, the client himself or herself can set the target objectives, and the design can be proceeded in such a way that those target objectives can be made. So the current field or the emerging field is the performance-based design approach, but we will not be going into detail into that. And one final slide before concluding our first chapter is a short introduction to the IS 456-2000 code, and that is the code of practice for plain and reinforced concrete. This is the code of practice that we will be adopting in this design course. So this code was first published in 1953 under this title here, Code of Practice for Plain and Reinforced Concrete for General Building Construction. Although in the beginning this was marked out for building construction, but now this code IS 456-2000 is the general code for all concrete works for all types of construction. So this is the fourth revision of the code after its first publication in 1953. Fourth revision was made in the year 2000, so it is IS 456-2000. And then the limit state approach that we will be using to design our reinforced concrete structure. This limit state approach was included after the third revision of this code in 1978. Previously, working stress design was adopted, but now this working stress design method has been moved to a particular annex in this IS 456-2000, and the limit state approach is adopted here. So this code is divided into 5 sections. Section 1, general. Section 2 talks about the material, workmanship, inspection and testing. General design considerations are given in section 3. Special design requirements for structural member and systems are given in section 4, whereas the structural design including the limit state method, that means limit state method, has been discussed in section 5. So the code has been divided into 5 sections, and 5 amendments have been made to this code. After its revision in 2000, 5 amendments have been made in June 2001, September 2005, August, May and July 2019. So the latest revision is the 5th amendment, or the latest amendment is this 5th amendment made in July 2019. We talked about this amendment, latest amendment, when we talked about the characteristic strength in our previous lecture. So 5 amendments have been made till date. So this brings us to the end of this first chapter. In this first chapter, we discussed on these 4 different topics. First, a general introduction. Then we discussed about characteristic strength and load. We discussed about the difference between analysis and design. We discussed the design process and basis for design today. And finally, we looked at the different design philosophies or design methods of RC structures. In next section or in next class, we will begin with the limit state design method. We will look at the working stress design method at the very end in 1 or 2 lectures, but we will start with limit state design in our next chapter. So that means we will start with our second chapter in our next video lecture. So we'll see you again then. Till then, stay safe and thank you.